believe we discussed KZG polynomial commitments. So just a quick summary of the costs here. So sort of very good for the verifier. The commitment, so this is, by the way, specific to univariate polynomials. There are analogs for multilinear polynomials, but they have somewhat higher verifier costs. So focusing on the univariate case, the commitment is just one group element. Evaluation proofs are also just one group element. And then checking the proofs is dominated by two pairing evaluations. So this, they need a pairing friendly group. And we discussed briefly the cost of this last week, I think. How expensive is a pairing? It's equivalent to about 10 scalar multiplications for one pairing, which is in turn equivalent to one scalar multiplication is like 400 group ops. So this is like 4,000 group ops. Group additions, if you're calling the group operation addition, which you could call about equal to one group operation is like 6 to 12 field operations. So let's just call it roughly like 40,000 field operations. And if you just want to know like how long it takes to run, this kind of checking procedure on a CPU or something, it's like should be like a millisecond or so, like single threaded. So just to give you a sense of how much work the verifier is doing here, ultimately it's very little. But if you do this on Ethereum, it's gonna cost you like tens of thousands of gas. So just to give a sense of how much work the verifier is doing.
Cool.
So
pause for context. Just kind of some questions about that.
Mm-hmm.
So you're bringing it down to like the field operations, and I guess we're just always thinking about we're breaking it down, right? When we're doing the pairing, we have to do a bunch of scalar multiplications, and those are raising it to like a high power. I think you were saying like that's when we raise it to a power that could be as big as like 2 to the 256, which is why that ends up being so many group operations. Sorry, go ahead.
Yes, yeah, all that's correct. We're switching sort of between additive and multiplicative terminology here, but all of that is right. Like a scalar multiplication is additive terminology, but if you use multiplicative terminology, this would be just be called exponentiations instead of scalar multiplications.
And it's called scalar multiplication because we're multiplying a number by group element. So we're adding that group element to itself a bunch of times.
Exactly. Yeah. So right. So with additive notation, by the way, it's very confusing. There's really no way around it. Sometimes additive notation is convenient. Sometimes multiplicative is convenient, and so there's just no way around like kind of switching between the two. So additive notation, we're dealing with a number times a group element. So this is really, when I say number, I mean an element of the scalar field of the group. But anyway, could think of it as a number. This is a group element. And multiplicative notation, this is literally the same thing, just a different way of denoting it. It'd be G to the C. And C, think of it as like, it could be as big as 2 to the 256 or something, like these numbers, can be huge, same as the size of the group or whatever. So you're exactly right. So as a result, that you would not like the way you would compute G to the C is like some kind of repeated squaring thing. Like imagine C was literally 2 to the 256. You compute G to the C by squaring G and then squaring that and then squaring that. And you'd have to do that 256 times before you computed G to the 2 to the 256. So it takes some getting used to, how expensive are, these operations. But this is a quick summary. Yeah.
The 256. So
Mhm.
because you've said the number 400 a few times, but you also just kind of walked through the worst case, and it was 256 operations, not 400.
Yeah. So actually, this sort of isn't the worst case. The worst case is so if you look at this number in binary, 2 to the 256, it's like one followed by 255 zeros. Okay. The worst case would be all ones, I guess. And just so what would that, so 2 to the 256 minus one would sort of be the worst, something like the worst case. And then what you'd see is you'd be doing, so this would be called square and multiply. Like the general algorithm is square and multiply instead of just repeated squaring. If you use multiplicative notation, this would be called multiply and add. Is it square and multiply and yeah, multiply and add, I guess. um, Let me keep using the multiplicative notation that I was using here. So yeah, what this repeated squaring is doing is like, you think of the exponent as being in binary. So initially you just have g to the 1, but then when you square it, like the exponent in binary becomes 1, 0. And then when you square it again, it becomes 1, 0, 0. And when you square that, so that's where you get 256 squarings. Is you're just sort of moving the 1 over in the binary representation of the exponent, until it reaches 256 trailing zeros, 255
You
trailing
have to
zeros.
build this number one like bit by bit, and it's the most tedious thing you can do. So okay, yeah,
Yeah,
but
yeah,
you're like
exactly.
building.
And so if you wanted to make all of these 255 zeros ones, I guess you'd do something like g squared times g. So this would give you 1, 0, but then when you multiply by g, you get 1, 1. And then you would take that and square it and multiply that by g, and that would make the exponent 1, 1. Like every square is like shift to the left 1 bit, and then every multiply by g is like replace the zero, the low order 0 bit with a 1. And so yeah, so the worst case is when the exponent in binary is like 256 ones. And then not only do you have the 256 squarings, you also have the 200 or 255 or whatever it is. You also have the 255 multiplies. And so 400 is sort of actually that's what's looking at the average case. 400 comes from saying, well, a random exponent in binary is going to look like every bit is just random. I'm just writing random bits here. And so half of them will be ones. And so you're going to have like 255 squarings. And then on average, 255 over 2 multiplies. And you add those two things up, what is this, 125-ish? And so 255 plus 125 is like roughly 400. So that's where my 400 comes from. All right, yeah. So just to summarize, so like one pairing evaluation is equivalent in cost to like 10 scalar multiplications. I literally could not tell you what is happening when you do a pairing evaluation. I just know that this equivalence is approximately true. Um, Everything else, I do know what happens inside of them. So 10 scalar multiplications, as we just discussed, each of these is like 400 group ops. And then, a group op can be implemented with like 6 to 12 ops, like multiplications over the base field of the group. And then if you want to go down to CPU cycles, this is typically something like 40 to like call it 80 CPU cycles. And so you multiply all of this out, it's roughly, this was like 40, I said 40,000 field ops. So 40,000 times 80 is what, like 320,000 CPU cycles. And so when I translate that to CPU runtime, there's like 3 billion clock cycles, per second, which is 3 billion is 300,000 times 1,000, right? Something like that. No, yeah. Well, anyway, I can't. So times 1,000 would be 300 million, right? So I guess it's times 10,000. So maybe one pairing, let's call it, is somewhere between, according to my calculations, 1/10,000 seconds and 1/1,000 seconds to give like a crude range. Um, and so, just call it like, very, very crudely up to an order of magnitude. It's like 1 millisecond. So in summary, through this long sequence of calculations, you can get roughly an estimate that like checking a KZG commitment is on the order of a millisecond on a CPU. It's two pairing evaluations. It's about a millisecond. Okay, so that was KZG commitments. I'd say the big downside of KZG commitments that we're going to try to address today by covering Dory. So one is they need a trusted setup. This powers a tau trusted setup thing, which, a lot of people don't like the sort of the trust assumptions of trusted setups. There's some toxic waste that if everyone who participated in the trusted setup ceremony got together and reconstructed their share of the toxic waste, they could, break any snarks that use the KZG commitments. Some people don't like that. I'm more bothered by the size of the commitment key. So this trusted setup generates what's called a commitment key, and it's big. So I think it's more, in my view, the performance implications of, having every, potential prover in the world have to download this commitment key is more bothersome and worrisome than the trust in the trusted setup. But that's a debate we will have, until we just, stop using elliptic curves completely because the quantum computers come or something. So anyway, so yeah, it also has a linear size commitment key.
While we're here,
Yeah.
could you mention if a transparent analog of the commitment key is it smaller in terms that a user would need to generate the same amount of data that commitment key requires to download?
Yeah, great question. So were this to be, a transparent elliptic curve based commitment scheme like bulletproofs or, like Dory we're going to see today is transparent, there would still be a big, a big commitment key, like the powers of tau trusted setup, commitment key. It would consist of many, many, many group elements. The difference in the transparent case is those group elements would just be random group elements. So the commitment key would be random group elements. And so there is a difference here, which is the way in practice you generate random group elements is you basically just take a cryptographic pseudo-random generator and evaluate it many times, so to get the ith group element in the commitment key, the transparent commitment key, you would like evaluate the pseudo-random generator at I, and the whatever seed everyone agrees on, for all I. And so the difference is, in the powers of tau case, you literally have to, any prover must literally like download the key, from, some, I don't know, server or something, whoever is distributing the key to the world. Whereas in the random case, any prover can generate the key on their own without downloading a lot of data. So they do have to store the key, but they're not downloading it. They're generating it like locally on their machine.
I see. And Dory is this kind of Dory will be this kind of approach, will it?
Yes, Dory will be this transparent approach, and on top of that, Dory, um, as we'll see, the key is much smaller. So rather than being linear size, it's square root. Yeah,
Thank you.
yeah. Thanks for the question. Okay, so KZG, yeah, so it's not transparent. That's a big downside. Its commitment key is linear size. So that's I consider that a big downside. Next week, I'll discuss further exactly why I consider that such a big downside. There are reasons that are not well known yet. Motivated by some upcoming work, which will be out next week. And then the other thing I'll say is somewhat slow evaluation proof generation, which we briefly discussed last week. It requires evaluation proofs in KZG commitments are basically another KZG commitment to like let's call it a random polynomial, of degree n minus one, where n is the degree of the original committed thing. And so this is pretty slow. And I won't go into the details again, but basically, if you commit to, if the original thing you committed to only has small coefficients, it's actually pretty fast to commit to because the coefficients are small. But even if the original thing had small coefficients, the evaluation proof requires committing to something with random coefficients, and that will be 10x slower to commit to than if the coefficients were small. So these are the three downsides, in my view, of KZG commitments: not transparent, linear size SRS, slow evaluation proofs. Okay, so today we're going to discuss Dory. I will say Dory is not popular today. It has some so while it addresses all three downsides that I just listed here, it has other downsides that have rendered it so far not popular. I think it might change in popularity, TBD, but definitely worth knowing about. So it's transparent. So these are the good things about it. The commitment key is square root sized. So if you want to commit to a univariate polynomial of degree n or multilinear polynomial with log n variables, the commitment key size in Dory is root n group elements. I guess it's 2 root n technically. And the evaluation proofs. Okay, so the prover basically evaluates the polynomial. Of course, there's no avoiding that. The verifier is saying, "Hey, tell me this evaluation of the polynomial." The prover at least has to evaluate the polynomial to even determine the answer. So that's linear time unavoidable. And then on top of that, the prover does, okay, let's say order square root n pairing. It's actually a little bit better, but let's say order square root n pairings. Okay, so this is one of the, depending on who you ask, this is either terrible or great. Let me explain. So we've just discussed that pairings are somewhat expensive. It's like on the order of 1 millisecond per pairing, maybe up to 10x faster than that, based on my back of the envelope calculations. But in that ballpark. So each pairing is like, think of it as like a giant constant cost. Right. So we're doing a sublinear number of pairings, but each pairing is really expensive. So I'd say sublinear is good, but but we're doing a sublinear number of really slow things. So the message is if n is pretty big, and I've been doing these calculations recently for the upcoming work that's going to be out next week. If n is really big, say more than, I don't know, 2 to the 22, which is a few million. Order square root n pairings is not a bottleneck. So it's like a low order approver cost. If n is really small, say less than 1 million or so, basically the fact that each pairing is pretty expensive kind of outweighs that there's a sublinear number of them. And so order square root n pairings, may be a prover bottleneck. Okay, so yeah, so high level point is, so this is like asymptotically, this is sublinear, cryptographic work, sublinear in n, sublinear in the size of the committed polynomial, and because root n is less than n. So asymptotically, this is like a lower. When n gets big, you can basically ignore this cost, but when n is small, because each pairing is like painfully slow, at least if you're doing a ton of them, you can't ignore this cost. And so, in a sense, the evaluation proofs for Dory are much better than KZG. KZG is like linear cryptographic work, actually slightly worse than that for the evaluation proofs. Here it's sublinear, but kind of the asymptotics only work out to be sublinear if n is decently big. Although 4 million is not really all that big in the scheme of things. So for today, let's call this a good thing. So so what we have here is let's call it very fast evaluation proofs. Again, for sufficiently big n, they're very fast. For small n, these pairings are terrible. Okay, so these addressed all three downsides of KZG commitments. Much smaller commitment key, no trusted setup, fast evaluation proofs up to the caveats for small n I just described. That's Dory. Okay, so let's see. So that was the comparison to KZG. Dory actually should be viewed as like a descendant of bulletproofs, also known as IPA for inner product argument. Remember, bulletproofs was also transparent. It had logarithmic size proofs. So, KZG, it's constant size. Bulletproofs, it's log size. The big downside of bulletproofs was a, linear, actually super linear, slightly time verification. So Dory just addresses this downside. So Dory verification is log time. Okay, so it looks like Dory is like just strictly better than bulletproofs. But it concretely it's not, because while Dory proofs are still order log n size, concretely they are something like 12x bigger. Okay, so asymptotically matches bulletproofs, but concretely, does not match bulletproofs. So I'd say these are the two reasons, as best as I can tell, people have generally, not embraced Dory. Is the proofs are much bigger than bulletproof proofs. Even though the verifier is much faster, that seems to turn people off. And unless you're committing to pretty big things, the evaluation proofs might actually be slow rather than fast. And actually, similarly, there's a bunch of pairings involved with committing in Dory, which can also be a bottleneck, prover bottleneck, unless n is big enough. So those are the trade-offs. So in a sense, it addresses all the downsides of KZG commitments and the main downside of bulletproofs. And you'd think everyone would use Dory because it just addresses all the downsides. But then if you dive into the details, there are these new downsides that seem to have dominated and led to Dory not getting used today. There is one implementation available. I guess it's more of a research implementation, but no one's using it in production. Okay, so that's the overview of the costs. Let me see if there are any questions. No questions?
No.
Great. Okay. Wonderful. So let's dive into Dory. We actually have to begin with something called AFCO commitments. This is the initials of the authors who came up with them. I guess this might go by other names as well. The AFCO paper or papers, because I think it was a merge of two different papers. The G is growth. I don't know. The A is Abe. Apologies to the authors. I don't know the other names in full. I think growth had a paper that might have gotten merged with the other authors. So the merge paper is something called like structure preserving commitments, and we'll see what that means in a moment. Okay. And so the way I think of AFCO commitments is the following. They're sort of like an advanced version of Peterson vector commitment. So let me just briefly remind you what a Peterson vector commitment is. So it's if you want to commit to a vector U of field elements, where this is like the scalar field of the elliptic curve group your commitment scheme uses, call that group G. The Peterson, I'm going to use additive group notation today. Dory is a descendant of bullet proofs. As we've seen when we covered bullet proofs, it's really nice to use additive group notation for bullet proofs because there are a lot of inner products everywhere if you use additive group notation. So if you want to commit to a vector U with a Peterson vector commitment, the commitment is just the inner product of U and the commitment key G. Where this little g is just consists of n random group elements. So that's a Peterson vector commitment. Again, so the committed vector here is a vector of field elements. Okay, so let's get to AFCO commitments. So what if you want to commit to a vector of group elements? So how do you commit to a vector of group elements? That's what AFCO commitments answer. Okay, and so now let me. I'm going to talk very briefly about a slightly annoying detail of pairing-friendly groups, because AFCO commitments intrinsically use pairings. A pairing is actually a map from a pairing takes as input like two group elements and spits out a third group element. Sorry, let me call it. So a pairing takes as input, a bilinear map takes as input two group elements and spits out a third group element. You do not have to know these exponents to compute the pairing. Maybe I don't want to say G. Yeah, I don't know. I'll just say G prime here. Okay, so here's the annoying detail. There's actually three different groups at play whenever you have a pairing. So this first group element, G to the A, this is actually G1 to the A, where G1 is in what's called the first group, capital G1. And this second group element is in, is like G2 to the B, where G2 is in the second group. And the output of the pairing lives in what's called the target group, G sub T. There are pairings where G1 equals G2 equals G3. These exist, but they're much less efficient, so people don't use them. Okay, so yeah, and so why do I bring this up? I bring this up because I want to say this. If AFCO commitments, as I will present them today, are actually like insecure. They're not binding in this case. AFCO commitments are not binding as I present them today, in the case G1 equals G2 equals G3, there's a way to make them binding in that case, but the costs go up. So nonetheless, I will. Life just gets much easier if I present them assuming G1 equals G2 equals G3, GT. The notation just gets much simpler. Okay, so with that out of the way, how do you commit to a vector of group elements? And so I'm just going to say that these are elements in G, where all three of these groups are just G. But remember, like in actuality, this would be G1 to the n. But for the rest, I'm going to denote, ignore that there's that subscript one. Just to simplify the notation. So for like another minute, maybe I'll keep around the subscripts and then they'll go away. So this is the vector we want to commit to. It's a vector of group elements. The commitment key is actually in G2 to the n, but again, I'm going to get rid of this subscript momentarily. And so the AFCO commitment to the vector of group elements we want to commit to is the following. So it's going to look a lot like a Peterson vector commitment, but different. Has to be different because Peterson commitments stick the entries of U in exponents, and that only makes sense if the entries of U are field elements, if they're like numbers. If they're group elements, then they're not they're not exponents. So here's the AFCO commitment. So we have a product over all entries of U. This is the target group product. Okay. Of the pairing evaluated at UI, GI. Okay, so that's it. Okay, so this is like an analog for Peterson vector commitments of GI to the UI. Okay, so it's like if UI were a number, if it were like an exponent, we could just stick it in the exponent of a group element, and that makes sense. And that's what Peterson commitments do. But if UI is a group element, we can't do that. So we need like another way to, okay, this was, let me go to additive notation, UI times GI.
Sorry, can I ask?
Yeah, please hop in. Yeah.
Yeah, I'm sorry to interrupt, but I didn't get why we just omit the indexes. Because you said it can be an issue for FGO not binding, and nonetheless we just omit the indexes, and will not that be an issue further?
Yeah, so it will be in the sense that firstly, no one uses in practice pairings where all three groups are the same. And secondly, even if you were willing to use them, this commitment that I just defined here would not be binding in that case. But as we'll see, at least if I present full details, which maybe I won't, Dory is just sufficiently complicated that if we carry around these subscripts everywhere, like the description of Dory will just like my brain cannot handle the mental load as I present Dory. If I have to remember like which vectors are in G1, which are in G2, I'm just not going to be able to keep track of that. So instead, I'm just going to assume that G1 and G2 are the same. But then in practice, they wouldn't be. Does that
so I'm sorry, but I think I just missed that U in G1 and G is in G2, and so that makes my question just a little bit silly. Okay, thank you. Thank you.
Yeah, no, great. Thanks for the question. Yeah. So, I haven't gotten rid of the subscripts quite yet. So, so everything is accurate that I'm saying so far, which is the vector we want to commit to is in, G1 and, G1 elements, and the commitment key is in G2. in Dory, we're also going to want to, sometimes have the vector we commit to be in G2 and, treat G1 elements as the commitment key. And so the fact that we're ultimately going to want to do both, commit to G1 elements and commit to G2 elements, is sort of exactly why things, my brain can't handle the mental load of keeping track of what's in what group, because, we kind of treat them identically in Dory, as we'll see. Okay. Great. So you should just think of AFCO commitments as like kind of exactly the same thing as Peterson vector commitments. It's just Peterson vector commitments commit to a vector of field elements, and with field elements, you can we got additive group notation here, but you can just have UI times GI, where this is a scalar multiplication. You're just doing the group. You're staying in G1 the whole time. But here you can't do that because the entries of U are themselves group elements; they're not exponents. And so how this is like multiplying a number by a group element. What if you want to multiply two group elements together? Well, pairings sort of let you do that. So that's what pairings kind of do, is they kind of let you multiply two group elements together. So that's why we have the pairing here. And then we just sort of munge everything together with the target group operation, because what comes out of the pairing is in target group. So if you ignore this product, what we have is n target group elements. And then to make the commitment, just a single target group element, we just apply the target group operation to multiply all those things together. Okay. So I'll just state a fact, which is this, AFCO commitments are binding under an assumption called the strong external Diffie-Hellman assumption. I think what's going on, I should have looked this up. I'm pretty sure this is just saying, I should have reminded myself, but I think this is just saying that the Diffie-Hellman assumption holds in G1. Okay. And so basically that this is like Diffie-Hellman holds in a pairing friendly group, because we need pairings here. I really should have looked this up, because there is a small chance I'm saying something a little wrong here. And when I said that AFCO commitments are not binding if G1 equals G2, we know that like this assumption cannot possibly hold if G1 equals G2. I won't go into the details, but so the Diffie, I won't go into the details. I'll just say that like we this is a standard assumption. We do think the Diffie-Hellman assumption holds in these pairing friendly groups. But that can only be the case if G1 and G2 are not the same group. Nonetheless, as I present Dory today, I don't want to keep track of what's in G1 and what's in G2, so I'm going to pretend that they are the same group. Okay. Questions? All right. Let me just comment on efficiency real fast. Okay, so while this looks a lot like a Peterson vector commitment, like it's not a Peterson vector commitment, and the difference is like for a Peterson commitment, if you compute the inner product between a vector U of field elements and a vector G of group elements, this is done by what's called an MSM, a multiscalar multiplication, and this is involves only G1 operations. But AFCO commitments, it's there are all these pairings in there. Remember, pairings are not fast. It's like 1 millisecond per. Like a G1 operation is way less than like a millisecond, whereas a pairing is like roughly a millisecond or something like that. So this is much slower. So this is what's called a multi-pairing. So just as the fast algorithm for MSMs is Pippinger's algorithm, like Pippinger's algorithm sort of also applies to multi-pairings, and so it's not quite as bad as n pairings. It's more like Pippinger's like kind of saves you a log factor compared to the naive algorithm. So this is more like roughly n over log n pairings about to compute this multi-pairing. Right. So like the naive algorithm would literally, go through each of these n terms separately, compute the pairing for each of them, and then apply the target group operation, n-1 times. You do not have to treat these pairings into the n pairings independently. You can kind of reuse work between them, and that's what the notion of a multi-pairing captures. But like n over log n pairings is like not a cheap thing. Like you'd much rather, like an MSM, like for Peterson is much faster. So a size n MSM is much faster than a size n multi-pairing. Okay, so these AFCO commitments, like they're pretty slow. Okay, and so for Dory to make everything fast for the prover, like we're not going to want to directly, it's not like we're going to want to take our polynomial with n coefficients here, and like we could just like do the following, right? We could treat all of these as so these are numbers, these are field elements, but like let's turn them into group elements so that it makes sense to use AFCO commitments. So you could replace CI, which is a number, with like GI to the CI, which is a group element. Maybe I should call it HI to the CI. And you could AFCO commit to, you could AFCO commit to these, define the commitment to this polynomial to be like the AFCO commitment, to now this vector of group elements, right? This is one way we could like kind of use the ideas underlying Dory to get a polynomial commitment scheme. I won't go into like why it would be helpful to turn these numbers into group elements. Just bear with me. If bulletproofs itself commits to just Peterson commits to these coefficients. Now we've introduced AFCO commitments, so you would only use them if the coefficients were group elements. So let's kind of make them into group elements in the AFCO commit. Let's just I don't know why we do that. Let's just say we do that. But this would be super slow. So, whereas bulletproofs, the commitment would, require an MSM of size n, AFCO commitments would require a multi-pairing of size n. Much, much slower. Okay, so we don't want to do that. All right, and fortunately with Dory, we won't have to. Okay. All right, so let's get to it. How does Dory actually commit to things? Okay, so now that we've seen AFCO commitments, let's talk about Dory. So I actually think Dory, as a refinement in a sense, this aspect of Dory anyway, is a refinement of Hyrax. Because Dory is sort of like a combination of bulletproofs and Hyrax, and it kind of gets the best of both of them. And so just a brief reminder of how Hyrax worked is, we took the n coefficients of the polynomial to be committed and we laid them out in a square. So the first row was like the first root n coefficients. The second row was the next root n coefficients, and so forth. Okay, and what Hyrax did was it took each column and a Peterson vector committed to each column. Okay, so Hyrax, the Hyrax commitment size was root n, because it was just like, one Peterson vector commitment for each of the root n columns. Okay, and that was a big downside of Hyrax. Okay, so I'll tell you what Dory does before reviewing how evaluation proofs in Hyrax works. So Dory says, well, look, the Hyrax commitment, it's big, it's size root n. These are group elements. Rather than actually sending all those group elements to the verifier, why don't I just send a commitment to them? AFCO commitments give you the ability to do that. So the Dory commit, to the polynomial, P with these coefficients is the AFCO commitment. So sorry, Dory commitment to P is the AFCO commitment to the Hyrax commitment of P. Okay, that's the power of committing to group elements, is like, you can apply a commitment scheme for field elements, which spits out group elements, and then you can commit to that. So you commit to the commitment. Okay, that's what's incredible about AFCO commitments. You can commit to commitments. Okay, and so first, yeah, please, question.
Yes, thank you. You just showed how Dory takes from bulletproofs and hierarchs, and now I wanted to ask about this commitment inside the commitment bit. If it would be a correct intuition to see this uh, like what you said about KZG in the beginning, that KZG holds another KZG to the degree n minus one in it.
Mhm. So I
Or
didn't quite get the question, I guess. So the KZG, has this linear size, commitment key, and it sort of it doesn't do any of this matrix stuff. It just lays all the coefficients out in one vector of length n, and sort of commits to it all directly with Peterson vector commitment. This Hyrax stuff, lays things out not as one vector of length n, but sort of as root n vectors of length root n. That's nice because you sort of never process a vector of length n all at once. That's kind of where a lot of the benefits of Hyrax come from. But the downside is the commitment is big. It's root n group elements. AFCO, Dory or AFCO commitments gets rid of that by then committing to committing to them.
yeah, I see. So it's just a coincidence and not an idea line behind this.
Yeah, I don't know. So yeah, I didn't quite get exactly what your question was, but I will say we didn't jump straight from like Hyrax and bulletproofs to Dory. There was an intermediate step. I don't remember all the authors' names. Maybe I can credit some of them here. I know Pratush Mishra was on it, and I think Benedict Bunz was on it, and Mary Maller and others. So apologies to the others. The paper is called it has the term inner pairing product in the title. Inner pairing products refer to these AFCO commitments. It's like we think of this as an inner product. So you would just call this like U inner product G, where now the pairing is providing you with like a notion of multiplication. And I guess that you would switch to additive group notation for the target group. So that they call that inner pairing product. I guess if I replace this product notation with a sum notation, it would look like an inner product. Sum of product of really pairing of UI and GI. So that was this paper, has the term inner pairing product in the title. And it was looking at, exactly this picture of like Hyrax, although I don't think, Hyrax, I don't think appeared in the paper, it was sort of implicit, but where the commitment to each column was a KZG commitment. And so I think your question might have been getting at, is it useful to combine, this matrix view of things with KZG commitments rather than, transparent bulletproof, Peterson vector commitments. And the answer is, people did do that as a predecessor of Dory. Asymptotically, I don't think it buys you anything, over Dory, but I think concretely it might, with I think this interpairing product paper, it has a trusted setup unlike Dory. I think maybe it's, I'm speculating here because I haven't looked at it carefully in a long time. I think maybe its proofs are a constant factor, smaller than Dory's or something. Still log size because we don't know. Yeah, but might be a little smaller concretely than Dory or something like that. So, there's a whole design space here where you can sort of, swap things out. You can kind of commit to these, columns any way you want, and you'll get something useful out. And there's probably, various pros and cons to any particular scheme you use to commit to the columns. Apologies if that had nothing to do with the question you had in mind.
It's very interesting. Absolutely, what I was wondering. You got the question better than I could express it. Thank you.
Okay, great. Yeah, thanks.
There's a question from chat which just says, like, is the commitment size of 1, or I thought it was square root of n?
Yeah, no. So Hyrax, it's square root of n. Dory, it's just one group element in the target group. So Hyrax, the commitment is 1, Peterson vector commitment per column. Dory, the commitment is an AFGO commitment to the Hyrax commitment, so that's just one group element. Was that clear, Abhi? Was that clear?
Yeah, that answers the question for sure. Is it like a general thing you can do? Is just commit your commit and make a smaller commitment, or is there? Yeah.
It is a general thing you can do. Yeah, if your first commitment is a bunch of group elements, then you can always AFGO commit to those group elements. Now, there's a cost to that, right? Like now, Hyrax doesn't need pairings, but if you want to commit to the Hyrax commitments, now you need pairings. So now, Hyrax had to work over a pairing from the group, so you could commit to the Hyrax commitment. And this brought in, like, the AFGO commitment to the Hyrax commitment did require the prover, to compute a multi-pairing of size root n, right? Right, the Hyrax commitment is root n group elements, and AFGO commitment to that requires computing a multi-pairing of size root n, which, as I was saying before, is like, not a prover bottleneck if n is big, but is a prover bottleneck if n is small. So if n is less than, like 1 million or so, that's going to be painful. And
am I sorry.
No, I would.
I just wanted to detail if I am correct that having this that applying this technique would also require much smaller set of curves, parent-friendly ones, and it limits the generality of the approach very much.
Yeah, I don't think so. I don't think it's very
problem?
limited in generality. You do need a pairing friendly curve if you bring in AFGO commitments. Hyrax doesn't need it, but if you want to commit to the Hyrax commitment, you need the pairings. But people are, BN254 is a pairing friendly curve that's an Ethereum precompile, and pretty soon there will also be a BLS 12381 precompile, which is another pairing friendly curve. So I think pairings are fine. If you're fine with elliptic curves, you should generally be fine with pairings. I will say, bulletproofs is a general inner product argument. Whereas Hyrax is like a polynomial commitment scheme. Polynomial commitment schemes are basically you only have to consider a special case of inner products where you're taking an inner product of the coefficient vector u with what I call the evaluation vector r, which in the univariate case would just be like powers of r. And this is a particularly nice vector, and Hyrax is exploiting structure in this vector. But on the, so, you know, you are lowering the generality a little bit from totally arbitrary vectors, you know, here to, you know, the kinds of vectors that arise in polynomial evaluations. But, you know, you can design any snark you want with just dealing with this stuff. So in my view, this is as general as one would ever need. Does that answer the question?
Mostly yes, and I would save a question for the end of this. It's quite tangent.
Okay, great. Sounds good. And I'll also mention, like, you could, Dory sort of has two orthogonal components. Okay, so one component I haven't discussed yet, which is basically take bulletproofs and make the verifier logarithmic time instead of linear time. Okay, that's one component of Dory. We haven't talked about that at all yet. The other component is sort of take Hyrax and address its major downside that the commitment is big. Okay, and the way it does these two things are completely different, and you just combine them. They're like orthogonal. You can combine them or not. And so if you took the bulletproof refinement part of Dory and left out the Hyrax refinement part of Dory, you would get a general inner product protocol the same way bulletproof is. Yeah, so in that sense, Dory is just as general as bulletproofs. But I think, like, you know, what the most interesting version of Dory does everything, right? It gets all of the good things of bulletproofs, but addresses its downside, the linear time verifier, and it gets all the good things of Hyrax and addresses its downside, the big commitments. Okay, so yeah, okay, so that's the commitment in Dory. Now let's talk about evaluation proofs here. So I told you what the commitment was. I haven't told you how, you know, the prover, you know, provides evaluations of the committed thing. So reminder of how evaluation proofs in Hyrax worked, right? So remember what the prover actually committed to was this matrix, you know, with the coefficients of the polynomial kind of listed, you know, first root n in the first row, second root n coefficient in the second row, and so forth. And so if the verifier says, hey, I want to know P of R, where P is the committed polynomial, you will hopefully remember that that's equal to a vector matrix vector product, where on the right we have like the first root n powers of R, and on the left we have powers of R root n. Sorry, my handwriting is illegible here. So I won't recap, you know, how you see that, but it's not hard to see that, you know, any requested evaluation of the committed polynomial is the same as taking the committed matrix and multiplying it on the left and right by, you know, two vectors derived from the evaluation point. And so what Hyrax did was let's call the matrix A, and the right vector, I don't know, I'll call it little b, and the left vector I'll call little a. Okay, so what the prover did was the prover just sent in Hyrax capital A times b. So it did one of the two vector matrix, you know, one of the two matrix vector things. And what the verifier did was it you know, so I guess it sent a vector, I'll call it little v, which is claimed to equal a times b. And what the verifier did was it homomorphically derived a commitment to the actual a times b, you know, by taking the column commitments. There were, you know, one per column, and you know, combining them to get a, you know, a times b is a linear combination of the columns. So the verifier using homomorphism can derive on its own a commitment to the linear combination of the columns, and then, you know, confirms that that this little v, which is claimed to equal capital A times b, indeed opens that commitment. Okay, and then once the verifier knows that the prover has correctly provided it with little v equals capital A times B, the verifier on its own can compute the requested the needed evaluation, because that's just A, the inner product of this left vector A with V. Okay, so that was Hyrax. Okay, and this was another downside of Hyrax. The commitment was size root n, but also this vector V has size root n. It's like the commitment size is the number of columns, and this little v is size number of rows. And so, kind of the way to minimize the total size of the proof or whatever, commitment size plus evaluation proof is to, equalize these two costs, make the number of rows equal to the number of columns. That's where root n comes from. So Dory needs to, we want to avoid that with Dory. Dory, we want logarithmic verifier calls. Okay. So what happens with Dory is actually the verifier on its own, can't even do this in the Dory context. So Dory V can't even do this, even if we were willing to give it root n time. So Dory V can't do this because it doesn't even know the column commitments, right? The Dory verifier only knows an AFCO commitment to the Hyrax commitment. Okay. So what is the Dory verifier? What is the Dory prover going to do? So Dory prover proves it knows this little v. Okay. Well, sorry, how do I want to say this? Dory, the Dory prover is going to prove it knows, okay, the following things. A Hyrax commitment that opens the AFCO commitment. And then it's going to also prove that it knows a vector v in what is that, field to the number of rows, which is root n. That, well, let's just say the vector v that the Hyrax prover would have sent and moreover that a inner product that particular v that it knows equals the claimed evaluation. Okay. So that's it. So it's like Dory sort of commits to the Hyrax commitments. That's the commitment for Dory. And then the evaluation proofs, it's sort of the Dory prover proves that it would have been able to provide a convincing Hyrax evaluation proof. Okay. And in that way, it never has to actually send the full Hyrax evaluation proof to the verifier. That proof is big. It's root n field elements. It's this vector little v. So the Dory prover basically proves it knows this little v without actually sending it to the verifier. Let me try to write it. I think I want to give this Hyrax commitment a name. I'm kind of running out of letters here. Maybe I don't know. Maybe I just call it H1 to H root n. Because there's one group element per column. So writing this out, let me write out these 3 bullet points again. So the Hyrax commitment opening the AFCO commitment. So that's equivalent to H inner product G, where this is the AFCO commitment key. Equals the Dory commitment, which I don't know. Again, I'm running out of letters here. I just call that com p. P was the original committed polynomial. Then the Hyrax verifier's check on this v was that v opens the commitment to A times B. So that the Hyrax verifier homomorphically derived. So this Hyrax commitment to A times B, if you write out what that was, okay, that was sum from I equals 1 to root n of bi times hi. Right. This was the homomorphically derived Hyrax commitment to a times b. So this was the inner product of h and b. Okay, so proving that the verifier would have accepted, the Hyrax verifier would have, accepted this V, that's equivalent to proving that V opens this Hyrax commitment. So now I need a name for the Hyrax commitment key, I guess, which I guess I'll call that G prime. Sorry, that you see why I don't want to like keep track of two different, groups, G1 and G2. I can't. There are too many, commitment keys living in different groups already floating around here. My brain is already fried, and we haven't even gotten to the second part of Dory that improves over bulletproofs yet. So let G prime be the Hyrax commitment key, the Peterson vector commitment key. Okay, so V opening this homomorphically derived commitment in Hyrax is the same as saying that V inner product G prime equals, right. So that that would be the Hyrax commitment to V equals this Hyrax commitment to A times B, which is H inner product B. Okay, and then finally I have here, that P of R is a inner product this vector V that the prover is proving it knows. So that let me just write that again. So writing this all out a third time without the extra notation as we go. Well, we have the prover's proving that it knows. Let's see, H was so G. I already forgot what H is. Well, we'll come back to it. So we had H inner product G equals the commitment to P. Oh yeah, this was the Hyrax commitment. So the prover is proving it knows this H. It's further proving that it knows this V, that V inner product G prime equals H inner product B, and then finally that A inner product V equals P of R. Okay, and so that's how Dory works. And what we have here is, let's see, we have we kind of need to prove two inner products about H. So we need to prove, what is the inner product of H with G and what is the inner product of H with B. We also need to prove two inner products about V. We need the inner product of V with G prime and the inner product of V with A. Okay. And that's where we invoke, can use sort of any, succinct, call it an inner product argument, any succinct, proof of knowledge of, of openings of, either Peterson vector commitments or AFCO commitments. That satisfy inner product relationships. Okay, but of course, AFCO commitments themselves, openings of AFCO commitments, that is itself an inner product relationship, right? Like saying, hey, I know a Hyrax commitment H that opens this AFCO commitments, the commitment to P. Well, that's just a statement about the inner product of H with the AFCO commitment key. Okay, so what I'm getting at is I've now told you how Dory works, up to telling you how one proves that they, so the remaining, part of Dory, which is, of course, a major thing that I have to tell you about is like, how do I succinctly prove, I know a vector, H, that opens a given AFCO commitment. Right, and this was exactly how I presented bulletproofs, right? I said, like, forget about polynomial codon schemes for a moment. Like I said, bulletproofs I presented as, exactly this, except AFCO was replaced with Peterson. Okay, and so that's also how I'm going to present Dory if I haven't used up all my time today. Let's see, we're hour 15 minutes in. I'll pause in a moment and think about whether we should end here and do a second session on how Dory works. Here anyway, I'll think about in a moment what to do. So I have told you how Dory works. Up to telling you how you succinctly prove that an opening of an AFCO commitment, right? So this whole Hyrax improvement thing boils down to just exactly that task, because I wrote out what does it mean for the if the Dory prover didn't send the Hyrax commitment and sent an AFCO commitment to the Hyrax commitment, how does the Dory prover prove that it would have been able to pass the evaluation checking procedure for the Hyrax thing inside the Dory commitment? Well, it boils down to a couple of a bunch of inner product things, and that's the same as just proving how to open an AFCO commitment in the first place. So yeah. And what is the benefits of going through this Hyrax route? It's the commitment key is of size root n, not n, because we can use the same commitment key. This is coming from Hyrax. You commit to columns. Each column has size root n. You can use the same commitment key to commit to each of those columns, and so that's a really nice property of Dory, that short commitment key. And then also because maybe it's not a benefit of Dory, but like largely avoiding a potential downside of Dory is that all of this really slow pairing stuff, these multi-pairings that are slow, they're only applied to the Hyrax commitment. They're not applied to the original committed vector. The Hyrax commitment has size root n rather than n, so the multi-pairings the prover has to do are only over vectors of size root n. Which means they won't be a bottleneck. You can basically ignore their cost for the prover as long as n is big enough. Good. So that's kind of the reason to do this. The reasons to do this Hyrax thing, and rather than running Dory without this Hyrax thing. Good. All right. So let me pause after that long rambling overview and see if there are questions.
Yeah, I got some questions coming.
Cool.
Can we go back to the point where we said that n, when being pretty big, isn't a bottleneck, and when it is rather small, it can be a bottleneck. Can you please again explain why is it the case? Because something should be a bottleneck instead when n is big.
Yeah, great. So what does the Dory committer or prover committer do? Because so what it does is it computes a Hyrax commitment. Then it AFCO commits to that Hyrax commitment. Okay, so depending on whether n is less than 1 million or significantly more than 1 million, one of these two things will be a bottleneck. And basically, if n is less than 1 million, then the AFCO commitment is a bottleneck. But if n is more than 4 million or something, then the Hyrax commitment is a bottleneck. Okay, so to unpack in slightly lower level, like what is happening inside 1 and 2, 1 is just like root n MSMs all in G1, each of size root n. And what's happening in 2 is a multi-pairing of size root n. Okay, so roughly, so really you should use Pippinger's algorithm to make this fast. Each of these MSMs fast, but roughly, I don't know. Think of this as something like something like n total, G1 operations. It's actually a little bit more than that, but don't worry about it here, just very crudely. Whereas this is root n pairings. Again, like crudely, there's actually a Pippinger speed up in both cases, and so on. And so it's like each G1 operation is like way faster than a pairing. Okay. On the other hand, we're doing way fewer pairings than G1 operations. Okay. So like which, there's a tension here in terms of what's going to be more expensive, one or two. It's like each G1 operation is cheaper, but we're doing more of them. So if n is big enough, it's sort of, the more of them thing dominates the that's it. It's like G1 operations versus pairings sort of are good for one being fast, but then root n versus n are good for two being fast. And so which dominates depends on how big n is. Does that clear things up?
Yeah, totally. Thank you.
Yeah. And I mean, I'll kind of go on, if this is maybe editorializing a bit, but I'd say the kind of the old generation of snarks, my perspective is they have very good verifier costs. I'm talking about things like Grow 16 and Planck and Marlin. They have very good verifier costs, very slow provers. Okay. And as a result, people only applied them to very small statements, very small circuits. Okay. And as a result of that, people tend to think of n as being like really small. Okay, but like it doesn't have to be. Like we can once we move to bigger, like better techniques that are faster for the prover, we can easily prove, bigger statements. And once we move to bigger statements, these root n pairings don't dominate anymore. So like I think this sort of thinking of like n is just not that big has kind of been holding Dory back unnecessarily. If we're able to handle bigger n, then you can basically ignore these root n pairings for the prover. And one of the, what I think people have considered to be a major downside of Dory, I think goes away. There are other downsides to Dory, like the proofs are an order of magnitude bigger than bullet proofs and stuff. So it's, what I'm saying might still not be enough to rescue Dory and make it popular. Also, there's like, of course, a lot of hype around post-quantum security, and nothing with elliptic curves is going to achieve that. But, in my view, for the next 10 years minimum, the biggest threat to snark design is bugs and not quantum computers. And so if we can get simpler, better snarks from elliptic curves, that will be more likely to be bug free. Than actually elliptic curves are much better than anything post quantum. So anyway, it'll be interesting to see how the next few years play out. But I am hoping I'm going to be pushing Dory a little bit, and we'll see what happens. Okay, more questions?
Yeah, I had one question. Can we go back to the list of things the prover needs to prove? The last one is fine. I have a question.
Here with 1 and 2, or no? Sorry, the list of books. Yeah, these three.
Yeah, that one. Yeah,
this list. Yeah.
So is that in there? The last one is the inner product between A and what B?
Yeah. So this is yeah. Okay. So let me change some color. So in I guess in pink, I'm going to circle things the prover is proving it knows.
Yeah.
But the verify are never materialized to the verifier. So in pink, we have the Hyrax commitment H. The verifier only knows an AFCO commitment to the Hyrax commitment. Okay. And then also in pink, we have this vector V, which you should think of as like the Hyrax evaluation proof, which if the prover is honest is this matrix A times this right vector little b. Okay. So these are the pink things are the things the prover is proving it knows, the Hyrax commitment and the Hyrax evaluation proof. Okay. Everything else, the verifier actually does know sort of in full, although things are a little bit hairy, as I'll elaborate upon now. So this was the Hyrax commitment key. Okay, now that has size root n. Okay, and so we don't want the Dory verifier to have to know a size root n object because we want the Dory verifier to run in log n time. So I'll address that. This gets addressed. The verifier, turns out, does not have to know all of this commitment key. I'll address that when we get to the inner product arguments that Dory uses. But in short, like the Dory verifier will not actually have to know this G. It will actually just have to know an AFCO commitment to G, which will be computed in pre-processing by any honest party. So this gets computed in transparent pre-processing. Right. So it's like, the the Hyrax commitment key is transparent but pretty big, root n size. We don't want the Dory verifier to have to, store a root n size object. So any honest party in pre-processing will compute a commitment to that Hyrax commitment key. And, it's transparent, meaning anyone who doesn't trust the party that computed that AFCO commitment can itself, just spend the root n time to compute it on its own and make sure, it matches or whatever. Yeah. So the Dory verifier, while it doesn't know G in full, it knows a commitment to G, and that's enough. This G prime was, I keep losing track of what everything is. This was the Hyrax evaluation proof. Yeah. Okay. This was the AFCO commitment key G, and this was the Hyrax commitment key. Sorry. So I just got, yeah. Anyway, I think the Dory verifier is going to have AFCO commitments to both of these things, and so what I just said about G will apply to G prime as well. And then finally, there are these two vectors A and B, which also each have size root n, but they're both fully specified by R, by the evaluation point R. So as we'll see, eventually, possibly not today, the Hyrax verifier, the Dory verifier, doesn't have to know, doesn't have to materialize A and B in full. It doesn't want to because they have size root n and it wants to run in log n time. They're very structured. If I tell you what R is, I'm sort of telling you what all root n entries of A and B are. So knowing R is enough for the verifier, for the Dory verifier. Okay. So yeah, to summarize that, and thank you very much for the question. The prover's proving it knows these two root n size vectors H and V. And then the other parts of these inner products that it's proving H and V satisfy are sort of public but kind of big. But it doesn't really matter that they're big. In the end, the Dory verifier won't need to know the whole root n size, orange, public vectors. It's going to be enough to either know AFCO commitments to those vectors computed in transparent pre-processing, or just the evaluation point R for the A and B vectors. Did that answer your question sufficiently?
Yeah, great. So basically, it's just not like in Hyrax we would send H and B, right?
Yes, Hyrax would send H and V explicitly, and Dory sort of sends
avoids that.
Yeah, it avoids that, exactly. Yeah.
Okay. Great. Thanks.
Yeah. More questions? Okay. All right. So yeah, we're probably 90 minutes in. So what I'm going to do is just give a brief overview of how the Dory inner product argument works. And then we'll wrap up for the day, and I'll think offline if it's worth going into more detail in next session. My guess is no. My guess is we've hit what are AFCO commitments. That's actually that in and of itself I consider like a win for the session. Like that, I think that's really meaningful, important concept. And we've also covered sort of how to think of Dory as like Hyrax, but avoiding the Hyrax downsides. So it gets the Hyrax benefits without the downsides. And now I'll briefly sketch how it's like bulletproof, but avoiding the bulletproof downside. And that's probably enough in the end. We can move on to the next topic. So yeah. All right. So Dory, the other core of Dory is a log size, proof of knowledge of an opening of an AFCO commitment. Okay, and remember, so if the commitment key is G, this would be a vector in, G2. I said I was going to drop the subscripts, but since I did that to be prepared for what I'm going to only sketch. And since I'm going to be so sketchy, it turns out I didn't have to go through that confusing I'm going to drop the subscripts thing. But anyway, so the commitment key is, a vector in G2, and the vector to be committed is a vector in, G1. Okay, and so, the prover is just proving that it knows U such that U inner product G equals whatever this commitment was. Maybe I'll just call that C. And this is inner pairing product, so I guess if I'm doing additive notation everywhere, this is sum of I equals 1 to N of pairing of UI and GI. Okay, so that's what I'm about to sketch. Okay, and so let's for a moment. So how does the prover prove it knows this U, where the proof has logarithmic size, and where unlike bullet proofs, the verifier runs in logarithmic time? Okay, so let's review what bullet proofs would do. But we'll and so what I'm going to do is point out like why is the bullet proofs verifier so slow, and then just say a few sentences about how Dory avoids that. Okay, so how would bullet proofs work? So in bullet proofs, you would be, a vector of field elements, but let's just, not worry about that. So what the bullet proofs would do in round one is the prover sends cross terms. So it breaks U and G into two halves. U equals UL and concatenated with UR. And G equals GL concatenated with GR, so the left and right halves of the two vectors. And the prover sends two cross terms. I call them VL and VR, which are claimed to equal UL inner product GR and UR inner product GL. Okay, and then what the verifier does is it picks an R at random from the field, and I might mess this up a little bit. I think I called it alpha actually when I present bullet proofs, and it kind of recurses on the claim that U prime inner product G prime equals C prime. Where, let me see if I can get this right. What is it? Okay. U prime is UL plus alpha GR. G prime is UR. G prime is, what? Yeah, I always mess this up. G prime is GL plus alpha inverse GR. And then C prime is the original C plus, alpha squared VL plus alpha to the -2 VR. I think I got this right. And so from the verifier, needs to know G prime and it needs to know C prime. Yeah, and of course only the prover knows U prime because only the prover knows U. So here we have, this is fast for the verifier, computing C prime is fast for the verifier. So here we have why the verifier is linear time. Computing G prime is the problem. Right. It's like, it was already a problem that I kind of said, hey, the verifier has to know what the commitment key G is. But like, why did the verifier have to know what G was? It was so it could like look at its left half and its right half and take this kind of random linear combination of the two halves. So this is the problem. Yeah. This is why the bulletproof verifier is slow. Okay. And so what Dory is going to do is in pre-processing, so this happens once for all time. What Dory will do is whoever is willing to do the pre-processing, anyone in the world can do it. In pre-processing, someone computes an AFCO commitment to GL and an AFCO commitment to GR. Okay, and in that way, rather than the verifier, so rather than computing G prime explicitly, Dory verifier will compute an AFCO commitment to G prime, which is AFCO commitments are homomorphic. That's what structure preserving commitments means in the original AFCO paper. They let you commit to commitments, commit to group elements, and still have homomorphism available. So, and because G prime is defined as GL plus alpha inverse GR, an AFCO commitment to G prime is just the commitment to GL from preprocessing. So let me call it AFCO GL plus alpha inverse times an AFCO commitment, the AFCO commitment from preprocessing to GR. Okay, and like it turns out in the end to be enough that the verifier, doesn't know G prime explicitly, but rather just knows an AFCO commitment to G prime. Waving my hands and hiding all the details like that. That's how Dory works. Okay, and so, what's going on here? And you have it, and the same thing will come up in round 2, right? So in round 2, the kind of the new commitment key for round 2, is G prime. That's what the whole point of round 1, like at the end of round 1, the whole point of bulletproofs was you reduced the original claim about U and a product G, which is 2 vectors of length n, U and G, to like an equivalent claim about 2 vectors of length n over 2, U prime and G prime. So G prime is like the new commitment key for the new claim of half the length. And so in round 2, you run into the same problem again, where the verifier, kind of the bulletproof verifier would want to know G prime left half and G prime right half. Okay, and it turns out that if the prover had separately computed commitment, like the prover, if the pre-processing phase, maybe I can sort of tell you in full what the pre-processing phase of Dory is. So you have this like original commitment key G of size n. I'm going to drop the subscript here finally because my brain is already fried. Which we write as G equals GL and GR. Okay, and then the preprocessing phase produced the AFCO commitment to G1, the AFCO commitment to GL and GR. Okay, and then separately we'll like kind of take GL and split that into 2 halves. Call it GL equals GL prime, I don't know, concatenated with GR prime, and we'll also commit to GL prime and GR prime, and then we'll take GL prime and split that into 2 halves, GL prime prime and GR prime prime, and commit to this thing and this thing, and then we'll split this into 2 halves. So in the end, what you wind up with is the following. So it's like the original commitment key had size n, so like n random group elements. That's like the kind of the bulletproof commitment key. And the preprocessing phase sort of takes those n random group elements, the totally random uniform group elements, and it kind of compresses them down. What comes out of the commitment phase is 2 log n group elements. Okay, and these actually, these are all AFCO commitments, so they all live in the target group of the pairing friendly group. Again, it's like what these are is like a commitment to the left half and right half of the original vector, and then a commitment to the left half and right half of, like one of those 2 vectors, and then a commitment to the left half or right half of one of those 2 vectors. And in the end, you have kind of logarithmic, phases of preprocessing, if you will. And this is the final verification key for the Dory verifier. Right. It's sort of, you think of it as like a compression of the bulletproof's commitment key. Bulletproof's commitment key was size n, and the bulletproof's verifier needed to know the whole thing. Dory, there's a pre-processing phase that anybody can do the work, and it sort of compresses that size n commitment key down to a logarithmic size key. The committer of Dory, of course, has to know the whole, size n commitment key, but the verifier of Dory only needs to know this log n size thing. Okay, and and so then if you look at what Dory's doing, basically everywhere in bulletproofs where the bulletproofs verifier would take like a random linear combination of two halves of some commitment key, the Dory verifier will kind of do the whole thing homomorphically underneath AFCO commitments to those two halves. That's roughly how it works. Okay, and in that way, you kind of just run bulletproofs, but just completely avoid the linear verifier time of bulletproofs. Now, why are the Dory proofs bigger than bulletproofs? Let me try to explain this briefly, and then we'll wrap up. That'll be it for the day. So I don't want to oversell Dory. There are these downsides. I talked about how the extra multi pairings the prover does upon commitment in Dory, if you're committing to big enough stuff, is not a major downside. But this downside that I'm talking about now is a real downside relative to bulletproofs. This 12x bigger proofs, like that really matters. So I don't want to undersell that. So what's going on is the Dory prover is sending like these cross terms. It's like, how do I want to say this? With that in bulletproofs would be G1 elements. In fact, bulletproofs doesn't even need pairings. So G1 is sort of a misnomer for bulletproofs, just whatever group you're using in bulletproofs. But in Dory are GT elements. I'm trying to think why that happens. My brain is fried. They're GT elements because AFCO commitments are all over the place in Dory. Okay, you can trace it. It might trace back to. I don't want to trace it any deeper than that since I'm fried. AFCO commitments are everywhere, so target group elements in Dory are everywhere. And these GT elements, one GT element in practice is 4x, bigger. Meaning more bits to express than a G1 element. Okay, so this is responsible for, when I say Dory proofs are 12x bigger or whatever it is than bulletproofs proofs, the fact that the target group is coming up, all of the elements are target group elements, that's responsible for a factor of roughly 4 out of the 12x. Okay, and then the other factor 3 is coming up because Dory, for reasons that I think I brushed under the rug in my description of Dory, because I was so hand wavy, actually sends 3x more values in each round than bulletproofs. Okay, and maybe I can just say a little bit about why that is. So this is coming from things I completely brushed under the rug, so I don't know if this is going to make much sense. I will keep it brief. It's like in Dory, if you started with the claim that I know a U such that U inner product G equals some value, I said the way Dory works is you turn that into an equivalent claim that U prime inner product G prime equals some other value. But there's this extra issue, which is in the Dory, the verifier only knows a commitment to G prime, an AFCO commitment to G prime. Yeah. Whereas in bulletproofs, the bulletproofs verifier literally knew G prime. That's why the verifier in bulletproofs was so slow, was to get that information. So there's actually an extra claim here in Dory that not only do I know a U prime so that U prime inner product G prime equals C prime, but also I know the verifier doesn't know G prime. It only knows a commitment to G prime. So the prover also has to prove that it knows a G prime, such that G prime inner product, the AFGO commitment key used to commit to G prime, I don't know what to call it G prime prime, equals whatever the AFGO commitment to G prime is, the commitment to G prime. So there's a second inner product claim that comes up in Dory that wasn't there in bulletproofs, right? In Dory, it's not just I know a U prime that has a given inner product with the vector the verifier knows. It's also I know, that second vector. Okay, and so that's why Dory, not only is it sending target group elements rather than G1 elements to the verifier, but it's sending just 3 times more elements in each round. So what Dory does is it has an extra step in each round that reduces these 2 claims, call them A and B, to a single claim. So basically, conceptually, like the Dory verifier in each round has an extra step where you kind of take a random linear combination of these 2 claims. And so that leads to the prover just sending more info in each round, because there's just this extra step where you have to reduce 2 claims to 1 that isn't there in bulletproofs. So you put those 2 things together and you wind up with 12x bigger proofs. On top of that, it's kind of gross that, like, I would much rather take 2 Peterson vector commitments, like VL and VR, and compute, C plus alpha squared VL plus alpha to the minus 2 VR with this. These are scalar multiplications, also known as exponentiations, happening in G1. In Dory, all of these are target group things. And so in bulletproofs, all this arithmetic happens in G1. In Dory, all of this happens in the target group. These are scalar mults in GT. Okay, and like these target groups and pairing friendly groups, they're just gross, right? Like it takes 4 times more bits to specify group elements. Applying the target group operation is just a gross thing. And so these are the actual downsides of Dory, right? That persist even once we're proving bigger statements than we were used to proving, a few years ago. The proofs get bigger. The verification procedures is involving all these target group operations. People don't like this. I think that you can deal with these downsides, and the upsides of Dory can far outweigh these downsides. And again, I will be elucidating this next week. And so we can talk more about it if people are interested then. Okay, so that's my coverage of Dory. Not the smoothest presentation, but hopefully you stuck with me most of the way. Let me know if there are any questions. And if not, we'll resume next week with a new topic. Questions?
I've got a quick one about preprocessing. Am I correct that it should be done not even for a particular circuit, but for a particular input to a particular circuit?
No, so the pre-processing, it's kind of like a power is a tau setup, like supports all circuits up to a given size. The Dory pre-processing lets you commit to all polynomials up to this size bound n, right? So it's like with powers of tau, right? Like I run the powers of tau setup once, and then I can run Planck or Marlin or whatever on any circuit, forever, as long as the circuit doesn't exceed the size bound that is supported by that setup. Dory is the same way. Yeah.
So I'll just think about it a bit more and maybe ask in the group. Thank you.
Yeah, sounds good. Yeah, I mean, I'll just say like one more sentence about how to think of it. It's like, if I want to apply Dory to polynomials, of size at most n, what I will do is I will use a PRG to generate n random group elements. Okay, and then I will run this pre-processing procedure that kind of compresses those n random group elements down to just 2 log n group elements, which are no longer fully random, right? They're kind of a compression of a much bigger object. And now anyone who wants to verify, Dory evaluation proofs ever in the future for polynomials of degree at most n, well, they only need to know those 2 log n group elements that came out of this procedure. And anyone who wants to prove, with Dory for statements of size up to n in the future, well, they only need to know, the n random group elements that I generated for my PRG, which they can generate themselves using the same PRG and the same seed. So that's how to think of Dory. It's transparent pre-processing, and it only needs to be done once for all time. And once you do it, you can, support polynomials up to degree n in any context whatsoever. It's just a degree bound. More questions? No?
Yeah, that's it.
No? Okay. Great. I don't know if that's good or bad, but
I think it's fine.
okay. All right. Great. Okay. So I'm actually I think next week I might start covering hashing based commitments. I don't think we've done that, right? I was trying to remember.
So for your information, like there is the SNARGs group, which is covering the book on that topic. So just I don't know how much overlap there would be with covering that. But
that's a good point. I'm pretty sure that book, I have to check. I think it mostly covers how you take hashing based interactive protocol and turn it into a snark via Merkle hashing and fiat Shamir. I don't think it covers like how Fry and Laharo and Breakdown work.
Cool. I doubt it. I don't know enough about those things to say with certainty, but like I think you're right.
Okay, so I will tentatively plan to cover like Laharo and Breakdown commitments next week, and probably Fry would be a separate session after that. But if anyone objects to that, either because we already covered it in this run through the study group and I forgot, or because another study group has covered it recently or something, just let Abby know, and Abby and I will discuss.
people are interested. So
okay, sounds great.
Thanks.
Okay,
Justin.
thanks everyone. Yeah, have a